Hi AB Calculus students, this is 2007 question number 5, and this is a table question. Later on this week you're going to be given the opportunity to take a quiz, and the quiz is going to have 3 different types of free response questions, and one question is this, and actually add 1.5. So there's actually 3.5 questions. 1.5 come from table questions. This question is insanely important, so please make sure you're paying attention, and you might have to go back and actually look at this video while you're taking the quiz. No looking up answers on the quiz, but you can look up your notes. So part A says estimate the radius of the balloon when the time is 5.4 using the tangent line approximation. Now, just a quick reminder, tangent line and approximation. If we have an x and a y, and a slope, we use the equation of the tangent line y minus, oh by the way, this normally comes from f prime x, and we do y minus y1 equals m times x minus x1. The first thing that might be slightly confusing here is that we don't have x's and y's. Instead, remember when we have a table, this is normally x, this is y. So our x in this problem is time, and our y in this problem is the radius. So you're going to keep that in mind. Okay, so in this problem, we need to know a point and a slope. So we need to know the point when time is 5.4. So when the time is 5... Oh, no. Oops, they said using the tangent line when time is 5. So when the time is 5, what's the radius? Well, we have to look in the writing. If you read the question, there's a big paragraph, and at the end of the paragraph they say the radius of the balloon is 30 feet when time is 5. So they literally tell you, let me bring it right up here. You've got to see this sometimes. Oh, and you can't see it. Never mind. Whatever. If you read the paragraph, they tell you when time is 5, the radius is 30. That's the point. The second thing we need is the slope. Instead of f prime x, it's r prime t. And we want to know what's the slope at time 5. So r prime 5 here you can see is 2. So now we can go ahead and write the equation. Now instead of y minus y1, it's r minus r1 equals m. My slope here this time is a 2. And then instead of x minus x1, it's t minus t1. So t minus 5. So this is the equation of a tangent line. And we're going to now find out what the radius is when the time is 5.4. So the first thing I'm going to do is I'm going to add the 30 to the other side to get r by itself, and then I'm going to replace the time with 5.4. And you do not need to simplify this. So this is the estimate for the radius at time 5. Okay, now they ask, is your estimate greater than or less than the true value? Okay, and you might get this on your quiz. You're going to have a tangent line on your quiz for sure, and you might get this next question. So is a tangent line an under or an over estimate? By the way, this is all for part A, sorry about that. It all depends on concavity. If a graph is concave down, tangent lines are over estimates. So if a graph is concave down, the tangent line giving us ordered pairs gives us answers that are greater. So concave down, tangent line is going to be an over estimate. And now let's look if it's concave up. If it's concave up and we use a tangent line, if you use ordered pairs on the tangent line to estimate real ordered pairs, you'll notice the tangent line is now below. So if it's concave up, tangent lines provide an underestimate. So the question is this graph concave up or concave down? And you have to read the problem to get to that. Oh, it says the graph of R is concave down. So, since it's concave down, so you would say, because RT is concave down, your estimate, concave down, the estimate is an over estimate. So again, tangent line approximations, concavity determines if it's an under or over estimate. And that's it for part A. And now let's go ahead and look at part B. So part B says find the rate of change of the volume with respect to time. Okay? I want you to underline this. Respect to time. You're going to be taking a quiz later on this week and you're going to see the word respect to time. Respect to time means related rates. Just as an example, let's take the area of a square. The area of a square is s squared. If you're taking the derivative of this with respect to time, everything gets a chain. The derivative of a would be dA dt, and the derivative of s squared would be 2s, but you get times the chain ds dt. So you're going to have a related rates question on your quiz, and there's one here right now. All right. So here they gave me the volume formula. 4/3 pi r cubed. To take the derivative with respect to time, we get dV dt is equal to, and the 3 goes to the front. When the 3 goes to the front, it's going to just leave me with 4. The exponent goes down by 1, and then times the chain, dr dt. Okay, now all we have to do to finish is to plug in the values. So they want to know the rate of change with respect to time at time equals 5. Well, we got to go back to the previous information. In the previous question, we found out when time was 5, the radius was 30. Remember, that was in the sentence. So if I want to know what is dV dt when time is 5, the radius is 30. And then what is dr dt? Well, dr dt, in other words, is r prime t. And we want to know what is r prime t when t is 5, and this is the same piece of information we used before. That is 2. So dr dt is 2. Do they ask us for units? Indicate units of measure. Yes, they do. Whenever you want to know units of measure, you simply look at what you found with the related rates. We found dV dt, meaning we found volume over time. So volume, in this problem, our units are feet. So volume would be feet cubed over time. And in this problem, you can see time is in minutes. So this is feet cubed per minute. Remember, we're not simplifying anything. It's this feet cubed per minute. The first problem, we didn't simplify either, part A. No simplifying. All right, let me erase this and we'll go to part C. Alright, so part C, they ask us to use a right-hand Riemann sum to estimate this. And they don't tell us how many intervals. Remember what a Riemann sum is. If I were to graph this, the graph, the ordered pairs, would look something like this. And what a right-hand Riemann sum does is it says for your first rectangle, you're going to travel up the right-hand side for the height. For the second rectangle, you're going to go up the right-hand side for the height, the right-hand side for the height, and the right-hand side for the height. So for each rectangle here, I need to see the base. So the distance between these is the base. So if this is a 0 and a 2, the base of the first rectangle, how far are these apart? That's a 2. So the base is 2. And with a right-hand rectangle, you pick the one on the right for the height. So the height is 4. For the second rectangle, 2 and 5, how far away those are? Those are 3 away. And again, we're using the height on the right-hand side, which is 2. For the next rectangle, 5 and 7 are 2 apart. And the height is, the height is 1.2. And last, we have even more. I apologize. I'm running out of space. So we actually have 5 rectangles. So from 7 to 11, that's a distance of 4. And again, we're using the height on the right, so we're using 0.6. And the last one, that's a 1, and the height is 0.5. And this is our answer. The estimate for this is this. We do not need to simplify it. Now it says, using correct units, explain the meaning of this. Now, it's really going to go really quick. I want you to think about position, velocity, acceleration. Okay? Position, velocity, acceleration. If my position was, let's say, in feet, and my velocity was, feet. Wow, unbelievable. Let's say this is feet. Can I go home now? Oh, wait, I'm quarantined. I am home. Okay. If the position was measured in feet, and let's say time was in minutes, so the derivative would be feet per minute. And then acceleration, the derivative would be feet per minute squared. Now, remember, that's taking the derivative. When you take so if you take the derivative each time, you get another unit of time on the bottom. That's when you take the derivative. But when you work backwards and you take the antiderivative, you lose this unit of time on the bottom. So if I take the antiderivative, it goes from feet per minute to feet. Now here we're talking about the radius. So instead of feet per minute, its antiderivative is simply, I keep wanting to put f of t. I am so sorry. There you go, feet. So it's this many feet. That's the area. Now, that's it. Part C is now over. I'm going to leave the answer up there though, and now we're going to talk about part D. So that's part C. Let's just leave a C here. So this is part C, and now part D. The question is your answer here greater than or less than the real answer? So they're basically asking, is this an under or overestimate? Now, when you're using right or left-hand rectangles, well, here we're just using a right-hand rectangle. So let's just look. If you are using right-hand rectangles, it's an overestimate if the graph is increasing. And if you're doing a right-hand rectangle, it's an underestimate if the graph is decreasing. So, left-hand rectangles and right-hand rectangles, or left-hand Riemann sums and right-hand Riemann sums, it depends if the graph is increasing or decreasing. With right-hand, because we're just dealing with right-hand on this problem, when the graph is increasing, it's an overestimate. When it's decreasing, it's an underestimate. You just run your experiments. So, in this problem, we have a graph. If you look at these, it is decreasing. Now, you would have to go ahead and read the question and make sure it was always decreasing. And if you read the question, you will see that yes, indeed, it is decreasing. So we would say this. Again, this is the situation we have here, is an underestimate because r prime t is decreasing. Oh, by the way, you might be wondering, how do I know it's decreasing? Earlier in the problem, we were told that r is concave down. And if r is concave down, the original graph r, if r is concave down, that means the slopes are always decreasing. Or in other words, if r is concave down, that means if you did a second derivative of r double prime t, if it's concave down, then r double prime t is always positive, which means the graph that comes before it is always decreasing. Okay. Anyways, that's kind of a weird question. So just quick recap. Increasing or decreasing will tell you if left or right-hand rectangles are over or underestimates, and you have to run an experiment. If you were using trapezoids, and you might have a trapezoid on your quiz, just really quick, if it was a trapezoid, it's dealing with concavity. If it was a trapezoid, trapezoids only, concave down is an underestimate, and concave up is an overestimate. But that's if it's trapezoids. This question was not trapezoids. All right, anyways, hope that helps. Talk to you later. Bye.